Alright, so in this video we're going to look at a special kind of change to a parabola which is called a stretch or a dilation. And I'm going to just take you through what it looks like and how we can calculate it and what effect it has on the parabola. So first of all, you'll notice that on this Desmos graph I have a table of values. I have all of my x values here. I have different rules. So this one is just a standard x squared. This one is 2x squared and this one is a half x squared. You'll notice that there's nothing added or subtracted at the end here, which means that the turning point is on 0, 0. All right, so first of all, I'm just going to join up all the green dots with a nice smooth, or as smooth as I can make it, curve like this. This is what they would look like. You can see here that they'll probably come through there and go around and then up to that one. All right, so that's the green ones making a nice curve. Now you can see here that the purple ones make a sort of a steeper curve, or a narrower if we were to compare it to the green one. It's inside at all times. All right, and then the black one you can see is outside the green one. So it's slightly, I don't know, fatter, wider, however you want to call it. All right, like so. Now this is the effect that the dilation factor has. And you can see here in this equation that A is the dilation factor. I think I've just moved that. Move it back. There we go. All right, so A is the dilation factor, and it is sits out here and multiplies to the x squared. So let's just have a quick look at what happens. Okay, I'm going to erase all of my purple lines here. We'll get rid of all of those curves because we don't need to see them anymore. What I'm interested in is a point that was on each graph and where it's gone to make the new graph. So let's have a look at an input or an x value of 1. So you can see here that x value of 1, standard one, is x squared, and that is just here. Okay, so there's x squared. Now, if I have a dilation factor of 2, that means that I square 1 and then multiply it by 2. And you can see there that the purple one has moved up. It's moved straight up to the new location of input 1, output 2. However, if I had a dilation factor of a half, you can see there that the output has moved down. It has moved to its new location of input 1, output a half, which was half of 1. All right, so to work that out, you would input 1 into here, so 1 squared is 1, and then half times 1 is just a half. All right, so there's no magic going on there, it's just order of operations. Now, the key thing that's happening is here, and the key way we describe it. You can see here that the point has moved vertically upwards or vertically downwards. It's not moving sideways or diagonally, it's moving vertically. So this is the big understanding from this lesson, that A value out the front of the x squared produces a vertical dilation, which you can see is the heading of my graph on Desmos here, vertical dilation. All right, so when you see an A value, you have to think to yourself, okay, so that's changed the parabola by stretching it vertically. It might have stretched the points up like this, in which case your parabola would be narrower than the regular one, or it might have pushed them down, in which case the parabola might be fatter than the regular one. All right, so two things, you can make them narrower or you can make them wider using a vertical dilation. All right, so I'll just erase all this and we'll have a look at a few other points and make sure that the same thing is happening. So let's have a look at input of a half. That's this green input here. So when I input a half into x squared, I get a quarter, which is fine. When I multiply a quarter by this dilation factor of 2, I actually get a half, so it's pushed it up. All right. When I multiply a quarter by a half for this other dilation factor, I actually get a smaller fraction, which means it's pushed it down, vertically down. So the same thing has happened. Let's have a look at an input of 1.5. Here's the regular input of 1.5. Squaring it just means it sits here. If I double it, I end up way up there. If I halve it, I end up way down there. Here's the input of 2. When I square 2, I end up with 4, which sits there. When I double 4, I end up with 8, which is just off screen. If I halve it, I end up with 2, which is just down there. So again, the same thing is happening. It's interesting to see that the changes, so if you look at the changes here, this is the halving change. That's rather small. This halving change is getting bigger as we go along. And the same thing is happening to the doubling change. That gap to that gap to that gap. And that's because you can see that the input doubling is an exponential growth. So because the squared function changes depending on the input, the doubling will also get bigger depending on the input. All right, now before I show you some calculations you can do to calculate A values, I'm just going to quickly show you on this graph. Here is the graph of x squared when A equals 1. So that's a dilation factor of 1, which means no change. 1 times anything is just itself. So effectively that's the same as saying there is no dilation factor. Now as I make A big numbers, you can see the parabola gets narrower. So this is numbers bigger than 1. It's getting narrower and narrower and narrower. All right. As I come back to 1, you'll see it hit the normal spot, which is just x squared. Then when I go into fractions, you can see that it gets fatter. All right, so there's A equals 1. Now as I come back down into the fractions, you can see that it gets wider or fatter. When I hit 0, it will be a straight line because 0 times x squared is just 0, so therefore there's no parabola. All right, and as I go into negative numbers, it mirrors the effect that you saw with whole numbers and fractions. So one of the key things is don't think about dilation factor as negative. A negative refers to the fact that the parabola is this way or this way, and the dilation factor, the number next to the negative, refers to the fact whether it's narrow or fat. All right, so dilation factors shouldn't be negative or considered to be negative. Okay, so that's the crux of the learning this morning, that the dilation factor makes a parabola narrow or fat. And now I'm going to show you how to calculate some of them, and then we're going to go back and practice some of those questions from our book. All right, so in each of the 3 forms, this dilation factor sits out the front of the, so in the first 2 forms, it's out the front of the brackets. In the last form, it's the coefficient of x squared. All right, now this is the same A in all of them. So it doesn't really matter which form you use, you'll be calculating the same dilation factor or A value. So choose the form that's relevant to the information you've been given on the page. All right, now what you would do is you need to choose the right form. So have a look at this example here on the left. We've got a blue parabola that has a x-intercept at 2 and a y-intercept at 3. So I'm going to use that information there. It's also the turning point, I notice, so I can write my equation in turning point form. So it's going to look like this. It hasn't been moved up, or the turning point is at 2, 0. Okay, now this is where I'm sitting currently. I don't know the A value, but I do know that there's a plus 0 in the end. Now this is where I look at the other piece of information they've given me and I notice that I haven't used it. So I'm going to use that now to calculate the A value, and I do it pretty simply by substituting that point in for y and x. So the location of this y-intercept is 0, 3. So now I can put the 0 in place of x and the 3 in place of y, and you will notice when I write it out that the only variable left in the equation now is this A value, which means that when I simplify everything, I'm going to be left with something equals A, and that will be my dilation factor. So let's go through and start simplifying. I've got 3 equals A bracket minus 2 squared. I'm going to leave off that plus 0 in the end because it does nothing. Next line down, I've got 3 equals A minus 2 squared is 4. 3 equals A times 4. I'm going to then divide by 4 both sides and end up with 3/4 equals A. So I've just calculated my dilation factor. I know that it's 3/4, which means that the parabola is a little bit fatter, just a little bit, than a regular parabola. The last thing I would do is to then write the equation of the parabola using the a value that I calculated in with the original equation that I made up. Notice now that my final answer has only got y's and x's in it, and a is now a number, which is what I was aiming for. So this is the full, most correct equation of the parabola, because the only variables in it are y and x. As a quick recap, first step is to write an equation using the info you've been given. Oops, that's not a very good V, is it? You've been given. Step 2 is to sub another point into I'll say this better, in for x and y. Step 3 is to solve, not having very good success today, solve for a. And the final step is to rewrite equation with a value. It doesn't really matter which form you choose from the outset, but I would stay away from general form, because then you'll need 3 points and to use simultaneous equations, which we will go into much later on. Don't stress about that now. So I would stick to either factored form or turning point form when doing this.